Good morning and good afternoon, everyone. Welcome back to Mr. Sniffen's geometry class. Today we're going to be talking about our extra special quadrilateral known as the parallelogram. Essentially the top of our pyramid of complexity for these kind of opposite sides or congruent, opposite sides or parallel type of figures. We've seen in our class discussion so far, we got our kind of our quadrilateral, our trapezoid, and then our parallelogram. Parallelogram is going to be our main focus for the next week or so. It's what kind of makes up our square rationales, our rectangles, our rhombuses, and the like. But let's go ahead and take a look at our notes for today. As usual, you got your homework due on Monday, give you a week of time, so please make sure that you get that in. This week's homework's pretty easy. But let's take a look at our lesson, our focus for today. By the end of the lesson, we should be able to define the term parallel or parallelogram, if you will, in your own words. In addition to that, what I'd like for you to be able to do is identify the properties of a parallelogram as well. Okay, so in a parallelogram, we have a series of attributes that get associated with it. First thing I'd like to state is, as we've seen previously, we are dealing with a quadrilateral. So we're going to have 4 vertices or 4 angles, 4 sides, that lateral portion. And in addition to that, when we're going ahead and naming our figures, we're going to kind of do so in a similar manner to the triangles. What we're going to try and attempt to do is go with whatever points the furthest left and the furthest up. The furthest left first would be in this particular figure, H, and then we're going to go counterclockwise around our figure. So in this example here, we have parallelogram HSRG, HSRG. Now, if you're seeing notes, questions, things like that, it's possible that the sequence can be written in the other manner, but then we're using an additional level of logic to kind of try and orient our figures back and forth. So that's why we tend to stay with counterclockwise and the furthest figure left. Let's go ahead and start to define this figure. Without any notations, it's a little hard to say specifically what it is. So what we're going to take a look at here is we're going to update our diagram here, and we're going to add some notations. What we can see in this particular figure now is that our opposite sides, our opposite segments, are essentially congruent. Here we have GR congruent to ST because of our tick marks. We see that GH is congruent to RS because they both have 2 tick marks. Now, one question that was asked for me earlier today is, does it matter how many tick marks? The only thing that the tick marks kind of represent is correspondence. So if you wanted to, you can put segment GR, you can put 50 tick marks if you want, but if HS is going to be congruent to GR, you're going to put 50 tick marks as well. So typically what you'll see is the smallest side has 1 tick mark. That's only because it's easier to design that way. So tick marks correspond, not too much to worry about here, but with parallelograms, those opposite sides are going to be congruent. Next, what we can say is our opposite sides are parallel. Now, parallelism is important. We don't necessarily always go ahead and assume parallelism dictates kind of side lengths, but what we saw with our equilateral triangles and our isosceles triangles is that once we start to connect a figure, we have certain systems that get generated. Once our opposite sides are parallel to one another, we end up creating some type of correspondence. Because if we don't have parallelism, we essentially have figures which don't have this interlocking relationship. Once we try to start to move the segments around and they're no longer parallel, we end up getting trapezoids, essentially. So as long as our opposite sides are parallel with one another, which we indicate using our arrows, which is our notation for segments being parallel to one another, we start to be able to identify a parallelogram once again. So as long as we can kind of hit any of these attributes where our opposite sides are congruent or our opposite sides are parallel, we end up being able to see that we have a parallelogram. Another thing that's kind of cool here is because of parallelism, we can describe our opposite angles as congruent So for instance, in this diagram, angle H is congruent to angle R, which you can kind of visually see like they both look acute. But what we saw with our trapezoid example as well, too, previously this week, is that our adjacent angles end up being parallel. What's a little bit different here is since as we go around the figure, we're kind of constantly going to parallel sides, every angle which is next to it ends up creating that 180-degree relationship. So for instance, angles H and G are supplementary, in fact, that they equal 180 degrees. But we can also say angles G and R as well. G and R would equal 180 degrees. G and H equals 180 degrees because H and R are transitive, almost, if you will, if we're talking about proofs. Lastly here is that our diagonals bisect one another. And what I mean by that is when they bisect one another is that when they cross, they hit each other at their own respective midpoints. When segment GS intersects segment HR, they hit so at point M, which is in the middle of those two segments. So in this example here, we can see that HM is congruent to MR, and separately, with a different measurement, GM is congruent to MS. So if we can kind of verify any of these three major groups that our opposite sides are congruent and we have a quadrilateral, or opposite sides are parallel and we have a quadrilateral, or we have a quadrilateral where diagonals bisect one another, most likely we're going to end up with a parallelogram. Just by our natural laws, by our laws of Euclid, this is essentially what we end up with. One last thing to show you here, one last kind of cool thing, is that since we're talking about parallel lines, we also have all those other relationships that kind of exist, like alternate interior, same side supplementary, alternate exterior, and the like. We just have to make sure that when we're drawing our lines, we do so in kind of like an intelligent manner. We don't want to like mislabel things, but as long as we have a parallelogram, we got our diagonals, aka our transversals, going through our opposite angles, we can kind of get all these relationships once again. All right, so once you have that down in your notes, as always, you can pause at any time. Let's take a look at some examples here. In our first question, what we're going to be doing is looking at kind of some examples associated with opposite sides. So here we're going to go ahead and say, like, if we're told we have a parallelogram, we know our opposite sides are congruent, the top and bottom, the left and right. If we're told that GR is equal to 7 inches, for instance, we can go ahead and say that HS is also 7 inches because they're opposite one another. And just so you know, you're picking up on the verbiage I'm using. Opposite means essentially not connected. We have the term adjacent, which means next to or touching. Opposite would be across the figure. So GR and HS are not touching, those are opposite. GH and HS are adjacent since they're touching, or they share a vertice, if you will. So let's try this in terms of like using a variable, if you will. In this example, we're going to go ahead and say that GR is equal to 3x plus 12, and HS is equal to 5x. If we wanted to go ahead and solve for x, what we are going to essentially do here is create an equivalency statement. We know the bottom is equal to the top, so we just set them with an equal sign in between each other, and we can solve for a missing variable. 3x plus 12 is equal to 5x. All we got to do is subtract our 3x over, leaving us with 12 is equal to 2x, or 6 is equal to x. So if we have congruency, we know that we can set these portions equal to each other. Just like in our original first unit, when we had something bisected, like a segment bisected, we know we can set up those equal signs. We're kind of doing the same thing here. Now we're going to look at opposite sides which are parallel. In our graph, we know that our opposite sides are parallel. We know we have a parallelogram because we have those arrows on our segments. So for instance, if we're told that GHS is equal to 68 degrees, we know our opposite angle, angle GRS, is going to be congruent to it. We get 68 degrees once again. We're going to use a similar example here to like our trapezoid we saw previously, where we can say our adjacent angles are supplementary. Once we've kind of verified that we have a parallelogram, once again, we can do that either by showing our diagonals bisect each other, our sides, our opposite sides are congruent, our opposite sides are parallel. We can kind of use these different rules here. And if we're told that angle GHS is equal to x plus 32 and HSR on the bottom right there is 2x plus 58, we know that they're supplementary since they're next to each other, or they're more likely in between two sets of parallel lines, that they're supplementary. So we can just set them equal to 180 degrees, go about our day, and solve for x as equal to 30. Okay, so let's look at just a couple more examples here. We're going to use that alternate interior idea that we've spoken about before. Here we're going to go ahead and say the angle GRH is equal to 47. Our alternate interior angle is going to be RHS, which we're going to describe as x plus 30. If these two angles are alternate interiors in that they're both congruent to one another, we can set up an equivalency statement where we say 47 is equal to x plus 30. And from here, we go ahead and just solve for our final value. All right, so one of our last questions here, we have diagonals bisect one another. Our diagonals are going to be segment HR and segment GS. You don't want to necessarily use the term lines because lines can't really be bisected. Lines are infinite. There's really no half of infinity. You can certainly write it out as an equation, but you know, it's still infinity. So we're just going to use our terminology for segments, and we're going to say segment HM in this particular example is 12x plus 20. MR is going to be equal to 14x. And if we want to go ahead and solve an equation with this, we'd say HM is equal to MR. Fill in our values here, and we get a final solution of x is equal to 10. So these are a few of the different examples that you would see. There aren't too many more. If we're to go ahead and do proofs, which we will in the future related to kind of parallelograms, we'll see some slightly different stuff. But once we can go ahead and kind of get these attributes kind of in our head, almost like as a checklist, if you will, similar to when we studied transversals and we went through and like almost flashcard wise, like described alternate interior, alternate exterior, same side supplementary, corresponding, vertical. All those rules still exist, and now we're way more comfortable with them. The more and more we practice these particular types of questions, the better we're going to be able to identify. So what we're looking for when we go ahead and identifying is if we see we have a quadrilateral and our opposite sides are congruent, we automatically guaranteed we have a parallelogram. Our next attribute would be our opposite sides are parallel. If we can verify that, say we have a parallelogram in a grid, for instance, and we just went ahead and did 4 slope equations, if you will, we can verify that manner. We can also verify this, say, if we're given the angles as well too. If we're given the angles of H and R, we know that they're congruent, and G and S are congruent. We can go ahead and assume we have that parallelism check mark, and we got a parallelogram. Lastly, when we see the diagonals bisect one another, this is going to guarantee congruency as well. The only way that this concept actually comes about and works is through that. Now, when we see something like alternate interior angles being congruent, we have to be a little bit careful. There are kind of some ways to modify figures where you're not necessarily always guaranteed to have these rules. So you want to be a little bit careful, because the alternate interior aspect gets generated just by parallel lines, and it doesn't necessarily mean that we have a parallelogram, because it doesn't account for the opposite angles. Say if we verify H and R are alternate interiors, what we'd also have to do is verify the G and S version as well too. So once we have each corner verified, then we're good. Okay, so that's it in terms of this particular lesson. I wanted to try and get it into you there for you fast. As always, these videos are posted up on YouTube, and you can always go back and watch them as many times as you want. Lastly, in addition to that, you're going to have some homework, and also make sure to check out Google Classroom for any assignments you might have. And as always, if you have any feedback, please feel free to email me. Let me know. I'm trying out a different microphone. I bought AirPods. Not too privy on the sound. I'm not a huge fan of it, but if you think it sounds fine, let me know. But until next time I see you, hope you do well. Make sure to wash your hands, clean your face. Please stay inside. It's New York City, it's coronavirus. All right, guys, have a nice day. Bye.